Hello, I'm Keith Rutledge, and I'm happy to have a chance today to talk to you about the edge and the emerging edge architecture. I am the general manager of EdgePoint at Compass Data Centers. EdgePoint is a startup within Compass Data Centers. Compass Data Centers provides data centers from the core to the edge, from 100 kW to 36 megawatts. And I'm happy to talk about where we see the edge architecture going and what we see happening today and the factors that are going to drive the transition. I believe there is going to be a very significant transition, and happy to talk to you about that a little bit today. On the screen now, what you see is the current architecture of data centers. There are actually about 3 million data centers in North America. That's everything from a wiring closet to a Google Hyperscale or Amazon Hyperscale data center. But the basic architecture is that we have some hundreds. Right now, we think about 500 hyperscale data centers in North America. And then you have regions, and the regions, in this case, include both the regional data centers for the hyperscalers and what we would normally think of as enterprise data centers. Enterprise data centers range from a few hundred kW to a few megawatts, maybe into the low tens of megawatts. But the point is, they are smaller than the hyperscaler data centers, and they tend to be geographically regional in nature. And then out beyond that, we have a few today, a few tens of edge data centers. So this data center infrastructure is reasonably evenly distributed. There are many thousands of regional or enterprise data centers. And then there are a few edge data centers, and there are very few core data centers, maybe 500. Where we see that going is to an architecture that's more distributed towards either end, towards the edge and to the core. So what we see emerging as a sort of a hyperscaler edge barbell type infrastructure. The middle will thin out. It'll thin out in terms of the number of data centers and the size of those data centers, and it will thin out in terms of the communications infrastructure. The communications infrastructure will more and more exist primarily to connect edge data centers to core data centers. I'm going to say this a few times during the presentation. If you can run your applications in a hyperscaler or core data center, you'll run them there. The economies of scale are real. The capabilities are real. It's more agile in terms of changing the application, meaning the software architecture. And there are compelling reasons, if you can run your application there, to run it there. The applications that are going to run out at the edge on the right side of our barbell distribution are going to be the applications that will only run at the edge. They'll have a set of requirements around latency. They'll have some technical requirements. They'll have required localism requirements that could be statutory or legal or otherwise. And so what can be done in the core will be done in the core. And what gets done at the edge is it can only be done at the edge. This next slide talks about some of the variables that are going to drive that. The middle column here shows the considerations or variables, and I'll talk about each of these and then come back to the outer columns in just a second. One of the primary considerations that we see driving the edge is IoT device scale. IoT devices vary enormously in what they are. They can be a refrigerator sending a few bytes to a customer service center for a manufacturer. It could be a camera. It can be an unmanned autonomous vehicle, whether that's airborne or terrestrial. So it could be a drone carrying passengers over New York City, or it can be a car in a mobility corridor. Literally any kind of device nowadays can be an IoT device, and devices can be multiple devices as well. I mean, your phone, at the same time that it's functioning as a phone, is also functioning as an IoT device in some cases. And so the scale of these is going to be, I think the technical term would be ginormous. If you look at what some of the bigger folks in the industry are saying, and some of the technical projections, we're talking about tens of billions, or and I think that may be a low estimate, tens of billions of devices for IoT. This basically breaks the internet. The internet scales to a pretty sizable organism today, but when we add tens of billions, 10, 15, 20 devices for every human being on the planet, then we break the internet. So that the device scale is going to be one of the most important considerations. A related but different consideration is payload size versus communication bandwidth. A refrigerator sending a few bytes to a customer service data center it's a small payload, and it doesn't matter how long it takes it to get there. It can take it a few milliseconds, it can take it a minute. As long as it gets there in an assured fashion, everything is fine. That's not true with a lot of other payloads, some of which are quite large. At the opposite end of the payload size and communication bandwidth criticality would be medical device or medical devices doing real-time operations. So I'm thinking about robotic surgery, for example. Robotic surgery, we have fairly large images, maybe running into high gigabytes or terabytes, fairly large images, and we have commands to the robot that depend upon the image being refreshed in real time to humans. I have a phrase I've used over the years called real enough time. And what it means is real time that is real, a time scale that is real to the consumer of the information. And so humans have a little bit of a latency in their response. As long as the device can respond in that less than human latency, it's real enough time. But when you talk about moving gigabytes or terabytes in real enough time for human beings, then you need a lot of communication bandwidth. And so the payload size, the IT payload size, which really means the size of the file data or other information, then communication bandwidth becomes an important fact. So communication bandwidth and backhaul avoidance turn out to be one of the most important linked variables for the edge. If we look at large payloads and the bandwidth it takes to move them in real enough time, we're looking at a pretty expensive proposition, building many, many, many very large network circuits from the IoT device to the core. And so then the expense of those circuits becomes sufficient to justify placing the computing at the edge. And so it's one of the prime economic drivers of business cases for the edge. And so the payload size versus communication bandwidth is one of our more important variables. Another variable, which is sort of in the same area, is whether or not the data or the application are ephemeral. Ephemeral means it doesn't exist forever. It comes into it's instantiated or comes into being, and then it goes away, and there's no permanent recording requirement. There will actually be a fair number of things like this. Things where it's important to execute the application, and there will be data created, but then it will just go away. And so if it's going to come into being, live for a few seconds and go away, and there's no need to record it, no statutory, no technical, no legal reason to record the results of that, because not everything, even today, not everything needs to be recorded, then why transport it back to the edge? And so I think ephemeral data, ephemeral applications and data versus permanent recording requirements is an important thing to look at as you look at the applications that are going to drive the edge. Rendering is another one. Rendering requires pretty significant amounts of computing power and fair amounts of storage. And so you can transmit the instructions or metadata to control rendering fairly efficiently, fairly small IT payload. But the rendered object itself can be quite large and require quite a lot of computation, and that's going to drive things to the edge a little bit. And then finally, and this is an important thing to keep in consideration, this is not so much that something is going to drive it one way or the other, but it's going to be important as we implement the edge. there is still a requirement for ACID uh, uh, transactions. ACID is a term from database technology. It means atomic, consistent, isolated, and durable. There are will be more and more transactions that span devices and span data centers. And as we architect the edge, and as we build out the edge, it's important to keep in mind that that's still a requirement. It's not sufficient for a check deposit to be recorded on my phone. It also has to be recorded at my bank and probably at a partner bank. And that's a single transaction, it's atomic. It has to be consistent across all of the places where it needs to occur. It can be isolated, and it darn sure needs to be durable. So ACID requirements are going to be there for sure, and it's important to keep those in mind. So as we look at core data centers, we'll cover those first. Core data centers absolutely, or hyperscale data centers, are really the same thing. They're at the core of the internet. And if you can conjure a visual metaphor, just as we did on the previous screen, they absolutely are at the core. They offer economies of scale. They offer economies of scale in personnel. You can use the same person to work across many different things. They offer economies of scale in real estate capital. They offer expense and operations economies of scale. They are more energy efficient. And as I said before, they offer agility in changing the application. If it can run in the core, if it can be done in the core, it will be done in the core. And I find in my discussions with clients that sometimes there's an emotional bias to doing it one place or the other. This is actually a pretty good test. Can I do this application in the core? If you can, you should, because it's cheaper, it's more effective, it's more agile, it's a better place to do it. If you can only do it at the edge, then you should do it. And of course, we'll do it at the edge because it's not a should. We can only do it there. So edge data centers, we see them coming into the market growing to support for a number of different reasons, to support IoT scale computing, to serve as aggregation points for applications where the data is ephemeral, to do caching and rendering. Edge data centers will create a sort of distributed resiliency. It's the N plus sort of resiliency. You know, if you have 4 cars, one of those cars is always going to be available. If you only have 1 car, maybe you have to share it among your family. Not a very good metaphor, I recognize, but I think everybody knows what distributed resiliency probably means. And then, as I said, required localism. There are municipalities and governments and states and provinces that have requirements to keep citizen data local or other kinds of data local. And so required localism is going to be an important part of the business case for the edge. And then latency. Latency creates a set of technical requirements for required localism. And so those are the trade-offs for the edge. If it can be done in the core, it'll be done in the core. If it can only be done at the edge, it'll be done at the edge. So this is what the edge at scale looks like today. We have some enterprise data centers. Some of those are in the core, running in the cloud, but they're really enterprise data centers, and they connect to my enterprise data center. So maybe I run some of my ERP applications in my own building, and I run my HR package in the cloud somewhere. But you know, it functions effectively as an enterprise data center. And so you have enterprise data centers that communicate with each other, and they create sort of a virtual or cloud-based enterprise data center. These can scale to hundreds of thousands of interactive devices. I almost said terminals, but what I really mean are interactive devices. They scale quite nicely to that today. Many of them can handle tens of millions of other type devices like phones or other devices. But what most of them cannot handle today, for many reasons, whether it's the communication bandwidth, the number of aggregation points, the capacity within the data center itself, or other reasons, they cannot handle today billions and billions and billions of other IoT devices. And so what the edge at scale tomorrow is going to look like is, we're limited a little bit here by the two-dimensional slide that we have to work with. What the data center is going, the architecture is going to look like tomorrow is we're going to have hyperscale data centers, and then those will run most of the applications that people use, the enterprise data center days, I believe, you know, in its physical form that a lot of customers run are fairly numbered. You know, they may be there for a few more years, but it is more effective to run them in hyperscale data centers. Some companies still have generators on site for backup, but very few companies generate all their own power. There was a time when they did. There was a time when every farm had a generator, but the centralization of power led to economies of power generation, led to economies of scale. And so those economies of scale led to companies not providing their own power. And the same thing's going to happen here with data centers. Hyperscale data centers have provable economies of scale in capital and personnel, in power, in real estate, and so it's, you know, it's going to win in the end. Then there's going to be at least 100, and I'm talking about North America here, at least hundreds of thousands, I believe, in the seven figures of edge data centers, and those edge data centers will be in a mesh communication network of sorts back to the hyperscale data centers. That's what I try to represent here on the chart. And that will scale to support the millions and millions of devices and billions of IoT devices. So you know, when you look at this, you really have to look at what a person like Satya Nadella said. This was back in the fall of last year, and he said to really understand the impact on the computing that the edge is going to have on computing, you have to look at how many devices are going to be. And he predicted, and as I said, I think this is a low number, he predicted 50 billion IoT devices on the edge. If there are 50 billion IoT devices on the edge, the current architecture of the internet in a lot of ways is broken, but one of the most important ways, and what we're talking about today, is the topography or architecture of data centers. And that will drive a shift to the edge for computing, and a shift, and at the same time, a shift to the core. So the barbell architecture I talked about earlier will emerge. And if you can do it in the core, you'll do it there. And if you can do it, if it can only be done on the edge, you'll do it on the edge. Economics always wins. And that's true in data centers as it is everywhere else.